G'day chemistry students. In this video we are looking at dot point 8.2.2 again. Our focus is going to be on mass spectroscopy, so a slightly different spectroscopic technique which will allow us to learn a little bit more about our unknown chemicals. Let's get into it. So first off, I'm going to start with the setup for a mass spectrometer. Hopefully that will help to make the spectra that you end up collecting make a little bit more sense and help us to understand what information we're getting and how we can use it. So essentially what you do is you start with your sample in this little section here, and you can see that we're using an electron gun. So our source of energy here are electrons, and the whole aim of these electrons is to ionize the substance. In this ionization process, what we have is the electron coming in contact with our mass. That can usually knock off an electron and cause the substance to have a positive charge. What can also happen in this ionization process is that the molecule itself can have its bonds split, breaking the substance up into smaller parts. We call the splitting of a molecule into parts fragmentation. So for example, what could happen is that electrons could be coming in. It may hit, say, the bond in between these two carbons and cause a fragmentation of the molecule itself. So for example, I might have one fragment with a CH3 group and then the other fragment with the CH2 group on the other side, but that might still be connected to a carboxylic acid group. Something else to note is that these will also be charged. And the charges on these particles are going to be really important to separate and analyze each of the fragments that we're making in this ionization step. So the next thing that happens is we repel all of these ions and shoot them through a tube, attempting to get them to hit this detector over here. Now the detector's not particularly sophisticated. It can't tell what the mass of every single particle that hits it is. So what we need to do is separate all of those different fragments that have different masses. And that can be done using an electromagnet and a curved part of the tube. The aim being for the electromagnet to selectively allow particular fragments to go exactly around the bend in exactly the right way, while making lighter particles get pulled towards one side of the electromagnet and having heavier particles not be able to make the curve all the way around, hitting the edges of the tube. So we can see this a little bit more closely in this deflection pattern that's here. Essentially, the one that's in pink shows all of the ions which have exactly the right mass to make the curve around. Lighter ions will end up being influenced by the electromagnet a little bit more strongly and get pulled further around than they need to be to hit the detector. And heavier ions are not going to be influenced by the magnetic field enough, so instead of going around the curve the right way, they'll just keep pushing forwards and crashing into the sides. What's important about the electromagnet though is that the strength of the magnetic field can change. So what the mass spectrometer can do is first have a really weak electromagnetic field to let the light fragments go through and hit the detector, and then get progressively stronger and stronger and stronger to allow heavier and heavier fragments to be able to hit the detector afterwards. What we end up with is a spectra that looks something like this. So we have an axis on the bottom which shows generally what the mass of each of the fragments are, and also a y-axis which shows us the abundance of each of those fragments. So the mass spectrometer itself, what it will do is set its magnetic field to allow for fragments that have a mass of, say, 1 to pass through and hit the detector and count how many there are. In this case, there were none. And then you move through all of these mass numbers one at a time to see if any fragments actually hit the detector. Here we can see the first peak here, meaning that the smallest fragment that was detected on this mass spectra had a mass of 27. There's also a few fragments that had a mass of 28 and another one that had a mass of 29. In between, again, we move and get a stronger and stronger and stronger magnetic field. None of the fragments really had any mass between 30 and, say, 38. But the next fragment that we get that gets a reading is 39. And we continue to move all the way through until we end up hitting this last peak here, an ion that can get through the electromagnet that has a mass of 72. Now what we can see from the title here is this is the mass spectrum for pentane. It has a molecular mass of 72, which is the largest peak that we see here, what we call the parent peak. And that's to be expected. If we were to just ionize pentane without breaking it up into smaller parts, we would expect to detect particles hitting the detector at that set mass of 72. So that peak makes a lot of sense. We also have a peak of 57. And if we were to do a little bit of math, what that would show us is that this peak here that we see would be CH3, CH2, CH2, CH2. Essentially, we lose one of our end carbons. And if you were to add up the masses of all of these atoms here, that would add up to 57. If we were to lose another one, that would give us a mass of 43, which matches with this peak here at 43, CH3, CH2, CH2. And the last one there, 29, would show a fragment that has one of the end CH3 groups and an extra carbon with 2 more hydrogens. So as we can see, each of these peaks do show us a part of the structure of pentane, and we can use that to analyze the structure of our unknown substance and maybe give us some information as to what type of particle it is or how it's constructed. Something else to note is that there's also been a label for what we call a base peak. We see that the peak for 43 has a relative abundance of what we would say is either 1 or like 100%. What that means is that the 43 fragment was the most abundant fragment that was present, and that the height of all of the other peaks are a relative comparison of how many fragments were detected for those compared to the base peak. Just keep in mind though that this abundance axis that we have here is not particularly informative, and we don't reflect on it too much when analyzing our spectra. Something else that I really want to highlight is the units that were on the x-axis, and that was an m/z or mz ratio. So in the deflection phase that we were talking about before with the electromagnet, the path the ion takes doesn't just depend on the ion's mass, but it also depends on the ion charge. So the idea is that the strength of the magnet will not be able to determine ion mass or ion charge, but just the ratio between the two. So what that means is if I had an ion fragment that had a mass of 100 but a charge of say 2+, it will be influenced by the electromagnetic field twice as much as a fragment with a mass of 100 and a charge of 1. And what that means is you could have one of these mass 100 charge 2+ fragments hitting the detector at exactly the same magnetic field strength as a fragment that has a mass of 50 and a charge of 1, because they both have an MZ value of 50. I will note though that something with a charge of 2 is not really something that you see too often in mass spectroscopy, and certainly for the purposes of learning mass spectroscopy in this course and the requirements that you'll have when completing questions, it's not something that you should see too often, if at all. Generally speaking, unless you've been told somewhere that the charge of a fragment is not 1, assume that it's 1, essentially meaning that most of the time when you're looking at MZ ratios, you can just assume that if Z is 1, that the MZ ratio is just going to be equivalent to the mass of the fragment, and there's no extra little math that you usually need to do there. Something else to point out is that different isotopes of elements will have an influence on their mass spectra. So usually when we're working with elements and they have their mass numbers on the periodic table, we're using an average of all of the isotope masses based on all of their abundances. And that can be really helpful for calculating things like molar masses and completing mole-based calculations. However, in mass spectroscopy, it's not so helpful because the machine, the mass spectrometer itself, is able to distinguish. It doesn't take measurements of individual molecules and just take, their average mass. It doesn't know that particular types of isotopes exist for different elements in differing abundances. It just takes measurements of things by the mass that every individual particle is. So what that ends up meaning is that we have pairs of peaks like we see for chlorine here. Chlorine has two common isotopes, chlorine 35 and 37, and they have an abundance of 76 and 24% respectively, essentially a 3-to-1 ratio. And that's reflected in the peaks that we see over here. So this taller peak here represents chloropropane molecules that have a chlorine 35 attached to the main chain, and the smaller peak to the right reflects a 2-chloropropane molecule that has a chlorine 37 bonded to the main chain. And what we can see is if we were to measure the relative heights of these abundances, that they would also exist in roughly a 3-to-1 ratio. So generally speaking, if you do see sets of peaks like this that have a difference in their MZ ratio of 2, similar to chlorine 35 and chlorine 37, and have two sets of peaks that are not equal in abundance to each other, but the two sets of peaks are roughly in a 3-to-1 ratio by their height, it's a fair assumption to make that there is a chlorine present on the substance that is being analyzed in the mass spectra. A similar thing can be seen for bromine. We have bromine 79 and bromine 81, which are in a roughly 50-50 ratio of abundance. What that means is when you start looking at mass spectra, like these ones that we've got here, and analyze key sets of peaks, what we can see is, again, that there are two peaks separated by a MZ value of 2, just like the difference in mass for our bromine isotopes. But in this case, the relative abundances of these fragments roughly exist in a 1-to-1 ratio. Same for these little peaks down the bottom as well. And that is because the abundance of bromine 79 and bromine 81 are also in a 1-to-1 ratio. At this point, you might be asking, well, hang on a minute, why don't we see lots of different peaks for carbon and hydrogen as well? They have isotopes too. And while that's completely true, the ratio of, say, carbon 12 to carbon 13 and 14 is extremely favored for carbon 12. And so because pretty much all the carbon that exists is carbon 12, with very little of it being carbon 13 and 14, you generally don't see a variety of peaks for carbon isotopes in a mass spectra. Same kind of principle for hydrogen as well. Hydrogen 1 is by far the most dominant isotope. Even though we have hydrogen 2 that exists, it's nowhere near abundant enough for us to actually see any fragments sort of crop up in a mass spectra. So when looking at our mass spectroscopy and reflecting on what it actually tells us, we can generally determine the mass of fragments or even the parent peak itself. And this can indicate some of the structures that are actually in the molecule and even give us an indication of where functional groups might be. Now, to determine what those actual fragments are, it's good to reflect on what the masses of all of our elements are, as well as some of the common fragments. So hydrogen always has a mass of 1, carbon has a mass of 12, oxygen 16, nitrogen 14. We also talked about chlorine and bromine isotopes as well. They could be considered too. For the fragments themselves, CH3 groups have a mass of 15. If you have an amine group, a primary amine group in particular, 16 is its mass. Hydroxyl groups are 17, carbonyl groups are 28. If we have a CH3 and a CH2, they're 29. Amide groups are 44, and carboxylic acid groups are 45. These might be things to look out for in particular when analyzing mass spectra. Thank you very much, everyone. In the next video, we're going to start to look at NMR spectroscopy. There's two different types of NMR spectra that we're going to be looking at in class, one for hydrogen and one for carbon as well. The first video is going to be much more focused on explaining how NMR works, and the video to follow will look at how to actually analyze those spectra. But until then, have a good one.